So I'm very glad to be here, a bit frightened, to be honest. I will explain what we are doing with FMI at Renault, and especially I will focus on optimization of our assemblies. At least for our use cases, it is not a global answer to optimization. Just to start, few words about Renault company. I put in this corporate slide few figures for people who love figure. I just would like to highlight one point, is that Renault Group is organized around 4 brands, and all our products and their development are organized around these 3 brands. So Renault for new technology and energy efficiency, Dacia for robustness at good pricing, Alpine innovative brand and exclusive vehicle, and Mobilize, a new brand dedicated to new services and beyond the vehicle. So the context of automotive is very challenging. Among our challenge, there is three ones I would like to highlight. The energetic transition. So Renault is investing a lot on this topic, and all our vehicle will be in the future hybrid or even fully electric. Software, this is a very, very big topic in Renault. If we look at the share of the software in the price of the vehicle, a few years ago it was 20%. It will be 40% in the next coming years. So it is a very big topic for us. And the last but not the least, it's about regulation and compliance. We are very strong in Europe to innovate regarding regulations. So we have to face with new rules, and we have to design our vehicle to be compliant with them. So in this context, we have to develop more and more complex vehicle to be compliant. We have to be very fast in their development because there is a lot of competition between car makers. And more than ever, simulation is a key enabler for our engineering teams. Regarding 3D simulation, it is something very mature, and this is, I would say, work as usual. But for 0D, 1D, and software validation, we are still in ramp-up phase today. Our idea at Renault is to rely on existing model in the company, developed internally or in collaboration with our supplier, and to assemble them into digital twins, so that we will be able to simulate more and more complex test cases and to enable inter-domain simulation. As an example, ADAS, we will bring together control logic for ADAS software and vehicle dynamics. The same for torque management or even thermal management. So today we are introducing more and more complex use cases based on 0D and 1D models. And to do that in an efficient way, we get organized, or we organize what we call simulation platform around five kind of assets to make work together in order to produce results. Obviously, the first one is digital vehicle. This is the core of our simulation. And digital vehicle is composed by physics model, obviously, but also with control model, so the embedded software in the vehicle. We make a clear boundary with driver or customer. This is sometimes models, and sometimes it could be a real driver when we consider some specific simulation mean. I will come back in a minute. But keep in mind that digital vehicle is only models for the vehicle, and if we need someone or something to drive the vehicle, it is another model, and the boundaries should be very clear. The same for the environment. So by environment, I mean the script of the simulation. So it could be event, it could be rolling surface, it could be surrounding traffic, and these models should be dedicated to simulate the environment. All these kind of models are usually model or embedded software. To run the simulation, we rely on simulation means. It could be obviously workstation or cloud computing, but in Renault, it also include test bed, it include driving simulator, it include XR simulation. So there is a large amount of kind of simulation mean. And the last but not the least, it is about assessment. So when we are doing simulation, we need to focus on what kind of result we want to get from the simulation. And assessment is something that represents the goal of the simulation. It should not be forgotten at the beginning. Everything is possible, everything should be connected all together to work and to produce results. This is the target of the architecture. It is very important to define it at the beginning of the simulation. It will enable the communication between all these assets, and it enable the good communication at lower layer to make the communication between each model or components possible. So for that, we need to rely on standard because models come from different fields. And if everybody come with this one format to be connected to the other model, it will be difficult. So at Renault, we try to use and reuse standard, and FMI is one very important to be used. We choose co-simulation basically because it is easy, it is simple to produce, it is simple to use, and there is no big issue regarding IP. It is a good level of IP protection. As this format is well supported by our software supplier, so it is Siemens, it is GT Power, it is Simulink, obviously. This is something very natural and well supported by our supplier. Something very important also is about license. Some software editor make us pay for model design, but not for model simulation. And FMI, in some circumstances, can optimize our license cost. So probably the most obvious benefit is about interoperability and the fact that FMI will be is very clear about interface between each component. So currently we are using FMI version 2 as co-simulation, as I mentioned, because it is the most supported version among our editors. If we look at the simulation platform diagram, in some circumstances, we can consider assembly of digital vehicle, its driver, simulation environment as an assembly of FMUs. I won't discuss about how many FMUs, how we break down the architecture about modelization. I just focus on how to make efficient FMUs assembly. If we take an example, it is about thermal management. We consider, for this example, it is easy, very easy example because all models are white box. So it's very easy to make a comparison between ad hoc assembly with co-simulation tools. It was AMESIM and it was Simulink. It is our former way to proceed to make ad hoc simulation platform. If we compare with the same platform as Assembly, as FMU, sorry, there is many benefits to doing that, but there is also a big issue. First one is how to compile each model into FMUs. There is some software modeling constraints about the time step during the compilation. It is a case for Simulink, for example. We have to compile FMUs as fixed step. So we have first to convert all model into FMU, and we have to cope with some constraint doing that. And there is the big question, what would be the co-simulation step size at simulation platform level? This is a big question. If we are applying this approach on this model, we for a 2 hours driving cycle, we had 4 hours in a co-simulation simulation from our way, and we have a factor 10 when we are considering FMU. This is not acceptable. Even if we can build this platform quickly, the result is not good. So this is an old known problem about co-simulation step size that badly impact the simulation performance. And if we choose a bigger co-simulation step size, obviously the simulation is faster, but the accuracy is not there. If we look at this problem more deeply, we can see that in our simulation platform, two FMUs are very tightly linked. It is e-motors and battery and vehicle dynamics. And the thermal part is something very slow. So there is no need to have a high refresh rate. So we have to deal with the fact that all FMUs should communicate at the same time because there is one FMI importer and one co-simulation step size. And some FMU need high refresh rate and some other don't. So the trade-off for the choice of co-simulation is impossible here. What could we do? First approach could be to have a variable co-simulation step size. It seems to be a very good idea on the paper, but we need to find a good algorithm in order to choose the co-simulation step. And there is two pain points. First one is that some FMU don't support at all variable co-simulation step size. It is a fact. And for driving simulator, it is very difficult to consider variable co-simulation step size. So it can be deployed on every means. Another idea would be to introduce multiple co-simulation step size and make communication between some FMU fast and with other FMU slower, I would say. It seems to be a good trade-off between performance and accuracy, but it seems to require additional effort to design this assembly and to build the assembly itself. Anyway, we will see in the rest of the presentation, it could enable multi-threading approach computation during the simulation. We'll see in a minute. For that, we would like to introduce FMU containers. It is not a newest idea, but we apply it on our simulation platform. So basically, FMU container is, on one hand, a standard FMU. It implements FMI API. So here, FMI 2.0. It could be imported by any FMI importer. And it exposes some data needed by the rest of the simulation. And in other hand, FMU container could be seen as a FMI importer itself. It implements a kind of very small solver that convey value from FMU to another one inside the FMU container. And this very simple FMU importer can load embedded FMU and can even expose data exchange between embedded FMU as local variable. The point is that the two FMI importer work at different refresh rates. That's the point. So if we apply this approach to our thermal model, so we switch from a flat assembly of our FMU toward a hierarchical assembly, and we grouped e-motor and high voltage with vehicle dynamics, make them communicate at very fast refresh rate. And the rest of the simulation is at 500 milliseconds. It is sufficient for thermal phenomena. Doing that, the results are pretty good regarding the performance and even regarding the accuracy. In the graph at the bottom of the slide, we see there is some discrepancy between the reference simulation and the flat or even the hierarchical assembly. With the flat assembly, this is due to the fixed time step we are obliged to use during FMU compilation. and due to the co-simulation itself. Anyway, from I would say thermal team, the results are acceptable. Now, if we look more deeply in FMU importer implemented in the FMU container, in fact, there is two ways to run the simulation. So let's take an example with 3 FMU. We would like to embed in 1 FMU. We could consider execution of each FMU in parallel sequence. I mean that at each do-step time, each FMU will retrieve the data and make their own computation and update, I would say, the buffer inside the FMU container of the FMU importer. This is the first approach. It could be very useful because it enables parallelization. Each FMU execution is independent, but it will imply communication delays. So it is something very well known. When we execute a FMU, there is a one-step delay among execution. There is a second mode, which is sequential. If we know the order of execution of FMU, then we could run them in sequential mode. It could be very useful to minimize delays between FMU, but you lose the ability to do multi-threading. In our example, the parallel approach is very good. It is the one I just show the result. But the benefit of this approach of parallel sequence is that it is possible to use multi-threading. It is rather easy to use one thread per FMU, so that the CPU will be used at maximum during the simulation. In our example, this is not so great, because to have a good benefit of this approach, you have to have a good CPU balance among each FMU, which is not the case here, because we can see that e-motor and high voltage FMU is something very slow, and vehicle dynamics, it is a very simplified model, is very fast. So we cannot expect big benefit here because the load balancing is not so good. Anyway, as I said before, FMU container is a standard FMU. So you could do FMU container off FMU container and so on. That's what we did in this example. And so doing that, it has been possible to enable multi-threading at each level, and each FMU has its one thread to be executed. Doing that, the results are pretty good because we reach good simulation duration. So we are even faster than co-simulation between AMSIM and Simulink. Regarding the accuracy, we are very lucky because introduce delays between FMU, even reduce the gap between the original simulation and the FMU-based simulation. As I say just before, making FMU container is something that seems to be very efficient, or at least for us, but can be costly regarding the architecture and the container building themselves. So in order to solve this second point, we develop our very small framework to build FMU container. So based on existing FMU, based on a routing table, so it could be CSV, could be JSON file, we can build container, even at multi-level, very quickly by one command line. This tool supports also SSP, version 1 as I released, but we can even use SSP file in order to build FMU from SSP itself. This is something we released under open source license. It could be used for free, you can contribute. And it is something daily used on a Windows computer at Renault nowadays. Our future plan for this tool and this approach is to establish the link with MBSI, or MBSI is the mirror of MBSE. So we would like to use Katia Magic in order to design our simulation platform. And we would like to be able to produce quickly container from Katia Magic graph. And today we are working to port this tool to FMI 3.0 because our next challenge is virtual ECU simulation. So for that, FMI 3.0 plus layered standard would be very, very great. Just a nice feature I would like to highlight about this tool is the ability to expose technical data from FMU container. As we implement a very small FMU importer inside the FMU, it could be very easy to expose even technical values. And one of them is about performance. So when you build your container, you have access as local variable to value of exchange data between FMU, but you can have, in addition, access to RT ratio, what execution time of each FMU embedded in the FMU container. This was my last slide.